Good morning, good afternoon, good evening, everyone. Thank you very much for joining this IBPSA session 8 on room acoustic performance prediction. I'm glad that Ardeshir has agreed to offer this, the second one in the series. He did offer one in the past, which is now available on the YouTube channel. This webinar will also be recorded and would be available in near future on a YouTube channel. Ardeshir will talk about room acoustics, and basis of this would be the book which is published by IBPSA or endorsed by IBPSA, which is also available on the net. Taylor and Francis are the publishers. Ardeshir will talk about the subject for next 30 minutes or so, and then we'll take a question and answers. You will be able to send your questions online by typing in a question pane. I'm going to moderate questions, and I will see if somebody wants to ask question directly to the web to the Ardeshir. Will be able to unmute them so that you can ask the question directly. I welcome Ardeshir. Ardeshir, thank you very much for offering this one more time on the IBPSA platform. And over to you, Ardeshir. Hello, Ardeshir.
Thank you, Rajan. Thanks for inviting me, and hi, everyone. I'm very pleased to be here and share with you some thoughts about the acoustics in the built environment, and specifically talk a bit about the room acoustical performance. I assume that I should start here, so to speak, from the basic concepts and then work ourselves through the issues that are more related to computational acoustics. So the overview of the talk is as follows. I will be talking a bit about the acoustical applications in the built environment, and talk a little bit about the foundations of acoustics. So if you are already acoustical experts, I request indulgence about that part. Then we talk a bit about the acoustical design and performance criteria, and lastly, talk a bit about modeling methods and tools, and reflect about them. So acoustical applications in the built environment, in the building performance simulation community as a whole, and also in the IBPSA community, maybe is not as present as, for example, energy consideration or thermal performance simulation, or visual performance issues, or fluid dynamics and CFD. Maybe one reason for it is that the relationship between this factor and, for example, economical consideration is not as transparent, as maybe because of that people don't think about it always as a priority. Or if you think about complaints associated with performance of buildings, or issues that are critical with regard to the performance of the built environment, acoustical issues always quoted as some of the major contributing factors, for example, to dissatisfaction. So I think generally we need to consider those factors next to the other factors that are important to building performance simulation community, such as energy or thermal comfort. Interestingly, also scientists have shown that specifically with regard to the perception of people and internal information processing, there is, so to speak, a coupling between these factors. For example, acoustical perception of conditions can be affected also by the thermal situation in a room. And those interdependencies and interrelationships are something that also make consideration of the acoustical aspect an important issue. Generally speaking, we talk about the considerations of acoustics in the built environment in terms of the outdoor sound propagation, very relevant in terms of, for example, the impact of the noise exposure due to, for example, traffic noise, vehicular traffic, or aviation and noise. And those issues, of course, need to be considered in regional planning, in urban planning, and also in building envelope design. Another area which is more the subject of this presentation deals with the quality of sound in architectural spaces, the intelligibility of, for example, speech or music, speech performance, or the quality of music performance is one aspect of room acoustics, but also conditions, for example, in open plan offices, are something that is typically considered and addressed within the framework of room acoustics. Very important, of course, also the so-called building acoustic that deals with the possibilities of noise propagation within built structures through the airborne noise propagation or impact noise propagation, and the, so to speak, problems that occur when inhabitants on one unit of buildings are disturbed in their living or working processes by noise originating from other parts of the buildings or from outside. So those are addressed in conventionally we put those issues under the heading of building acoustics. So in order to have a basic grounding in discussions of building acoustics, it is important that we take care of a number of issues. One is, what are the main dimensions of the so-called acoustical space? I mean, traditionally, we talk about acoustical space as a virtual multi-dimensional space in which the relevant parameter associated with sound events are captured. As most of you know, we talk about these acoustical events have certain properties, such as the frequency, which is associated with the wavelength of the sound. They have some energetic capacity or intensity that is subjectively associated with the loudness. They, so to speak, evolve in the time dimension, so they have temporal patterns. And also they have complex combinations of multiple waves in musical sense, for example, in terms of harmonics, that gives something like an acoustical correlate of what we in visual terms refer to as color. So those are also basic, if you want, trust of how we describe an acoustical environment. The wavelength is very important in also acoustical computations because the range of the wavelengths, the dimensions that we encounter in room and building acoustics are very significant in terms of the interactions of the wavefront and objects, be that obstructions in the sound propagation field or be building elements that reflect and absorb sound. So that interaction is fairly complex. It is dependent on the wavelength and the frequency, and it also represents some of the challenge that we face in modeling of the environment. As you are aware, we are, as human beings, we are responding or perceiving a certain frequency range at about 20 to, in the case of young and healthy people, 20,000 hertz. But for most acoustical application, a limited or a subset of this frequency range is of interest. Noise control about 50 to 10,000, in room acoustics about 60 to 8,000, and in building acoustic roughly from 80 to 4,000 hertz is the range of the acoustical events in terms of frequency that we take into consideration. The energetic aspect, the energy associated with the sound events are typically captured either in terms of a sound power, if we talk about the capacity of the source to generate acoustical events. If we look at the, so to speak, energetic impact of a sound at a certain distance from the source, we can use the notion of intensity, which relates the sound power to a specific area. And for typical measurements, usually local fluctuations of the sound pressure. This amplitude is measured and is referred to as sound pressure. And as most of you are aware, we use typically in acoustical specifications not the units of power and intensity and pressure, the classical units directly. In most cases, we use the sound levels. So we represent the sound power, intensity, and pressure in terms of a logarithmic scale. In that, we use the measured values. We make a reference to the threshold of hearing of people, and we derive from that this logarithmic scale, and we express the intensity or the sound pressure or the sound power level in terms of the decibel units. And these decibel units are somewhat more, so to speak, easy to deal with in communications, and they provide a good overview of the energetic aspect of the acoustical exposure. So the definition of that is fairly standard, and most of you are familiar with that. Likewise, we can look at fluctuating events in the acoustical realm in terms of the energy content over time, having expressed the intensity of such events over time in terms of numbers that kind of provide an energetic equivalent of a fluctuating event, such as, for example, traffic noise. A very good view to obtain an overview about the basic properties of acoustical exposure is to look at the frequency domain. Basically, a frequency spectrum expresses what is the intensity of the event as a function of the frequency. And you can have then dynamic versions of the frequency spectrum over time and follow, so to speak, the evolvement of acoustical event dynamically over time. It's a very good view to obtain an overview. As far as our acoustical perception is concerned, it's a very complicated, very interesting, very dynamic feature. And surely we cannot just talk about that in a very short time. But generally speaking, our perception of the acoustical environment with regard to the physics fundamentals of that is quite nonlinear. We are more receptive to certain frequency. That means lower levels of energy sufficient to create an acoustical perception in the mid-frequency ranges. For example, the language or most of the musical experiences are considered. Towards low frequency, our ear is, so to speak, less receptive and less sensitive. And this nonlinear, so to speak, property is usually depicted in literature in terms of the equal loudness curves. Also, we are very good in detecting typically the location of a sound based on a number of issues. The fact that we hear binaurally, so we have two ears, and the distance of those ears can detect differences in arrival of sound, and that plus some other factors like the shadow effect of the head itself allows us to be fairly good even in those spaces in order to detect the orientation of the sound. Most importantly, we also got to be very conscious about the fact that the perception of the sound and the acoustical quality of environment is not exclusively determined based on the energy or the physical property of the sound. We associate with the sound many more psychological and emotional responses, and that affects the evaluation of acoustical environment. The same acoustical signal, depending on the context and the person who's generating it or perceiving it as annoying and noise, and for some other people it might contain some information and not be negatively attributed. So that is something that we have to take into consideration. The energetic features or properties of the sound field are a necessary condition to explain its impact, but it's not sufficient. And that's something that need to be kept under consideration. What about defining the essential design issues and performance criteria in these areas? As I mentioned before, in the area of building acoustics, it is important to consider how we actually can dampen the propagation, how can we reduce the propagation of sound, because it's typically considered or perceived as noise. So neighborhood noise, traffic noise, noise coming from other units of a residential building, those are typically considered of not containing interesting information and hence are negatively evaluated. So in this case, the construction and the design needs to address possibilities to reduce that coupling of the, so to speak, source and the receiver of such exposure. The design can, for example, look at how the layout of a building can successfully separate noise-intensive and noise-sensitive rooms. So that is basically a design issue in terms of the layout. However, we also have obviously a construction solution that can help improve the sound insulation, both the airborne sound insulation, transfer of sound from a source room to a receiver room, or the impact noise or impact sound transmission, which involves the direct mechanical agitation of a separation element, like a floor construction, for example, between two, let's say, residential units that are placed on top of each other. So the quality of construction solution can reduce that type of coupling. And in order to express the quality of the relevant building components involved, indicators such as sound reduction index for airborne sound transmission, or, for example, the notion of impact noise levels can be used. They can express the capacity of building components or entire solutions, construction ensemble, to reduce the unwanted sound transmission from one point in a building into another, or from outside building to inside. With regard to the room acoustics, where we are talking about the acoustical quality of the indoor climate, which is very important for rooms that are meant for acoustical communication, like lecture rooms, classrooms, rooms for cinema, performances of music. For those type of rooms, this acoustical quality is important, and in order to capture the processes that are involved, we need to be aware about the impact of the form, the geometry, because that geometry determines a number of issues with regard to the sound propagation in the room, if it's uniform or not, if there are unwanted concentration of the sound energy in specific spots in those rooms. But also we need to look at the properties of the, for example, surfaces in the room, in view of how much and in which way they reflect, absorb, or transmit sound energy. Incident sound energy typically can be reflected to a certain amount or absorbed, and that can have a direct effect on the resulting distribution and characteristics of the sound field in a room. So in room acoustics specifically, we look as a definition of the sound absorption coefficient as the fraction of non-reflected sound energy divided by the total incident sound energy on a building component, for example, or on a material. And the product of this absorption coefficient and the area of the element constitute the so-called equivalent absorption area. And as you all know, if you have large amount of absorption area in a room, you usually have an acoustical impression, roughly speaking, that is somewhat dampened. In extreme fall, you have an anechoic chamber, or if you have very little sound absorption area, then you have a very lively so-called reverberant condition. There are many different solutions for the type of absorption that can be either explicitly designed to be placed in a room, or implicitly is just simply available because the rooms are furnished with classic materials. We can look at those materials in terms of how much sound energy and in which frequency they absorb, and that knowledge is obviously also important when you try to model the response of a room to, for example, acoustical events, performances, and so on and so forth. The most basic representation of that information is that you got to know for a room that you are planning to model, what is the sound absorption coefficient, and in which frequency, what fraction of the sound energy is being absorbed. In terms of the quality criteria, as I mentioned, that information allows for you to predict also to a certain degree what kind of sound distribution do you need to expect in a room based on the geometry. As I mentioned, if that distribution would be rather uniform, we generally appreciate if there is a certain uniformity in a room that is passively, so to speak, is provided with sound energy. That uniformity is generally appreciated as a good characteristic. Geometry and the distribution of the sound absorbing materials defines to which extent that goal is achieved. Obviously, this quality also is expressed, historically speaking, through various performance indicators, as we have performance indicators in other areas of building performance. If you think about thermal area, we talk about, for example, heating and cooling demand. In the area of lighting, maybe we talk about daylight autonomy. In the area of acoustics and room acoustics, there are also historically multiple performance indicators have emerged. One of the early ones is very well known, is the supine reverberation times, that provides a intuitive measure, very rough, very general, but a first useful impression of what is the response of a room to acoustical impulses. What is, so to speak, the time where the sound energy is, so to speak, decaying in this room, and supine use a measure of decay of sound and the time that is required for the decay of sound, such that the initial energy density is reduced in a factor of 1,000,000, so which is equivalent to 60 decibels. But the reverberation time, as I said, is just one amongst the many different and useful performance indicators that have been introduced in room acoustics. In the IBPSA book chapter, there is a table and there are some definitions. I will not go through those definitions in details, but today we look at multiple indicators to address various features of the expected performance with regard, for example, to the clarity, with regard to the intelligibility of spoken word, and the warmth of, let's say, musical performances, and these different indicators that can be computed to a certain degree, can be predicted, help us define those issues. Now, let's move to the part where we can maybe discuss some general approaches to how we can generate models of rooms and try to apply formalisms, mathematical formalisms, to analyze and predict the acoustical performance in various areas of environmental acoustics. In the area of building acoustics, which I talked about before, there are a number of methods available to try, for example, to predict the rate of the rate of sound transfer, or the predicted transmission of sound from one portion of a building to another, by taking into account the properties of the involved construction elements, such as walls and floor construction and so on and so forth. Some of those methods or algorithms are captured in standards. Different countries do have different standards in that area, and the idea thereby is to identify various transmission paths. For example, the direct transmission, if you want, from the source room to the receiver room via a partition element, be that a separation wall or a separation floor, and a number of so-called flanking elements, which involve the transmission of impact noise through, for example, the ceiling of a room into the ceiling of the room in the receiver room, and then the emission of this membrane, so to speak, in the receiver room. However, you could argue that these calculation methods are, which also look at, for example, the impact of a junction geometry. If you have a junction of a separation wall and a facade, where we talk about a T-junction, or you have a junction of a wall and a floor system, where we talk about a cross junction. Those type of calculation methods are, in the strict sense of the word, are not really simulations. They're usually kind of gray box models that use also measured data and some information about the basic properties of the involved building components, like, for example, their density and their areas, in order to estimate the resulting magnitude of sound transmission. So there are really more calculation methods and less simulation methods. And it seems to me that right now, especially at the commercial realm, we don't have really first principles numeric methods that, for example, would use finite element methods in order to simulate for entire room assemblies the complex interactions of the sound waves agitating a building element as a membrane, and then simulate the very complex overlapping forms of waves that can emerge in that element, can be bending waves, torsional waves. And even though in principle there are numeric methods available to address those issues, but because of the complexity and especially the frequency domain in building acoustics, they have not emerged yet as, so to speak, full-fledged numeric methods that you can pick up off the shelves. And it seems to me right now those methods are usually used by the researchers for rather limited models of, for example, basic assembly rather than whole building simulations. So in that area, practitioners are mostly still using these type of gray box empirically based models. When we talk about the sound propagation outdoor, and then later on about sound propagation indoor, there are the computational methods that are numeric, that are more detailed. We could argue that they evolved significantly and are also being used by practitioners. At a very basic level, you could also argue that the underlying physical phenomena are very similar when we talk about sound propagation in a free field, and then later on we talk about sound propagation in the room. Basically, we can consider that the airborne sound emission can be captured in terms of a source emitting sound energy with some directionality pattern. It could be obviously fully uniform, idealized sense, but it could also be directional. And then simply using the inverse square law, we could then predict the decay of the local intensity as a function of the distance from the sound source. There are, of course, some level of complexity that affect those basic predictions. For example, we know that the temperature-dependent layering stratification of the air has an impact on this propagation. Likewise, we know that the concentration of water vapor in the air, the relative humidity, has an impact on the sound absorption properties of the air as a medium. So those complexity has to be included, especially for outdoor sound propagation, because they can play a major role. We also obviously have to look at not just simply the isotropic uniformly sound emitting sources, but also different more complicated or more involved sound sources, because the resulting sound distribution field would be obviously different. We also move into another layer of complexity if we consider that because of the relatively wide, the relevant range of frequencies that are involved in environmental acoustics is fairly large. If I simply would compare that to the light emissions, when you do light simulation, you obviously do have the notion of how do I simulate different colors. But the method that you would use, for example, ray tracing and radiosity, would not be so much affected in terms of the complex geometric interactions. In room acoustics, we have this issue that the magnitude of the wavelength and the size of the buildings that, for example, act as obstructions or reflectors, that interrelationship is fairly complicated. Already, when you would like to look at the effect of the, let's say, a obstruction that is being used as a sound barrier between a source and a receiver, that there is already there a complicated relationship between the size of that barrier and the wavelength of the sound that is incident. As this little graph, which is based on measurements, illustrates, if you go to the ladder low frequency and long wavelengths, you will see that the diffraction effect, which basically in lighting would be introducing light into the shadow behind an obstruction, is much bigger. It seems that the lower frequency can overcome the shading effect of obstructions, and low frequency sound could be heard more intensively even behind an obstruction. And so this, if you want complex interaction between sound waves of different wavelengths and obstructions of different surface properties and different dimensions, is something that represents a challenge also in terms of the modeling of sound propagation phenomena inside buildings. In order to address that, historically, we have been talking about three basic, if you want, disciplines in room acoustics. The geometric room acoustic, which looks at, so to speak, a kind of pursuit of individual abstractions of sound being propagated in terms of rays, and see how the geometry of the space would impact that propagation, is probably the oldest discipline in room acoustics. Long before computers appeared, people used drawing methods in order to estimate that impact or that interaction. Statistical room acoustic was introduced late 19th century. I mentioned the Sabine, I mentioned the reverberation time. There, the idea was to not look at individual, if you want, idealized rays that are metaphorically representing the sound distribution, but look at wholesale energy consideration. What is the, let's say, mean energy density in a room, and what happens after an acoustical event? What happens to this energy field over time, and try to kind of pursue that line of reasoning is constitute the statistical room acoustics. The wave theoretical room acoustic is mathematically most demanding, and it would look at the impact of this with the wave nature of the sound field and resonance effects, and also the room resonance effects and three-dimensional effects associated with that, and try to understand that, which for straightforward boundary conditions can be solved analytically, but involves a fairly complicated, so to speak, mathematical apparatus to address issues in room acoustics. A relatively good way to obtain a picture of what happens in a room, so to speak, in more simple terms, in comparison to the free field, you could imagine that in the free field, you are basically using the inverse square law, and you're saying that, okay, by basically increasing the distance from a sound source, the energy density is reduced proportional to the propagation, so to speak, the wavefront. As the wavefront grows proportional to the square of the distance, obviously the energy density then reduces proportionally, something like 6 decibel every time you double the distance, and that would give you the basic tendency of the sound level in the free field. Now, in a space, you have obviously the response of the room, and statistically speaking, that response of many reflections by many constitutive surfaces of the indoor space, they would create a diffuse field. And what you then expect at a specific location is the superposition of those. And depending on if you have a room which has very little absorption, so most of the surfaces are hard, then you get a different, so to speak, diffuse field. You get a diffuse field that is strong. If you have a room that involves a large magnitude of absorbing materials, then you get more closer to what's going on outside, so you don't get a lot of response, and the diffuse field is weaker. So before we started to do computationally supported ray tracing, also this notion of splitting these two and predict them separately for standardized morphologies of rooms was quite common. In geometric room acoustics, of course, as I mentioned before, we can constitute idealizations of sound energy being distributed in a certain direction, and we can pretty much as we do it in the area of visual simulation, we can then pursue the destiny, if you want, of these rays. If you're talking about, for example, specular reflection, we can apply the Snell law and say, okay, the angle of incidence and the angle of reflectance are equal. Once that's the case, then you can create source images of multiple order, and that provides you with a convenient way to look at the distribution of the sound. So you can have first order image source images, or you can have second order and multiple orders. And in computational simulation, as long as you can assume that a surface is creating specular reflections, that is a, so to speak, smooth surface, and it is relatively large compared to the wavelength of the incident sound, then you can use the source image method in order to pursue the ray tracing and arrive at some information about what densities you expect at a certain point in time. It allows you to judge from the formal point of view also what is the impact of the shape of the room, the orientation, the slope of the surfaces, and in fact in design those can be used for special applications, for example large rooms for speech or musical performance, in order to optimize the formal aspects of the room, especially if it involves reflecting surfaces. You can also take that possibility in the computational realization to judge, for example, if reflections are useful. Obviously, the indoor acoustics benefits from the fact that the enclosure of the room is providing reflectances, because it intensifies and complements the direct sound component. That's the, so to speak, the advantage of having acoustical events within rooms. But if those reflectance arrive too late at a specific point, then they might be problematic. They can create, in the extreme case, echo, but also, even if not so extreme, they can create a kind of messy, so to speak, and not very well-defined acoustical sensation. So in order to do that for different applications, we allow for a certain maximum arrival time difference or path difference between the direct and the reflected sound arriving at a source, and a computational construction of those patterns of reflection allows us to see if, in fact, in a specific room, for a specific constellation of the source and receiver locations, do we have to expect such problematic reflections? And if yes, how can we address that? By maybe adjusting the orientation of the reflecting surfaces, or if applicable, by using sound absorption to address the problem. Traditionally, we have used this method in order to identify what part of a room enclosure for a given constellation of source and receiver provides useful reflections, and what part of the room might provide reflections that come too late and create effects that we would like to avoid. As I mentioned before, we need also to address this complexity, which is the relationship or the interaction of the wavelength, interrelationship of the wavelength and the nature of the reflecting surfaces, because the wavelength of sound in room acoustics can be very different. Very low frequency, you have multiple meters, basically wavelengths that are the order of magnitude of the room dimensions. And if you go to high frequency, we're just talking about a few centimeters. So you can have articulations in rooms that are big enough for very short wavelengths to create mirror reflections, But if we get to a point where these dimensions of these articulations are about the same order of magnitude of the wavelength of the incoming sound or incident sound, then we get diffuse reflections. So we need to address those interactions also in the simulations, otherwise we will not be able to simulate the effect of scattering of the sound by rough surfaces, or for example, the presence of objects, columns, and those type of furniture elements in the way that they they influence the sound distribution in a room. To address those, there are different possibilities. Most of you are familiar with the visual performance simulations. You know that ray tracing obviously is used massively in those, but also radiosity. Radiosity dealing mostly with the so to speak, the non-specular reflections. There are instances of both of these methods also being used in room acoustics. However, quite popular in most recent development is then one addresses the specular reflections through the source image method. For if you want a few orders, those are created. But in order to address the scattering properties of rough surfaces, or to address this wave and the dimension of the reflectors problematic, in those cases, also probabilistic methods are used. So the idea is that the energy being reflected after the sound bounces from the source can probabilistically be diverted from what is suggested by specular reflection or the Snell law, so that we can look at that information. And if you then do a Monte Carlo type simulations, that you could have a pattern that would be statistically representative of the behavior of that surface in dealing with the specific wavelength which is incident on the surface. So this is the method that most recent developments in acoustical simulations are deploying. I don't want to talk about specific programs. There are multiple programs that are available. Since we have been using one of these programs, so I just mentioned it, the Odeon program. The structure of these programs in terms of the input and output are typically go through a certain number of steps that I just quickly mentioned. You will start by defining the geometry of the room, either by some parametric modeling language, or you have some aiding tools that help you extrude a geometry, or you basically import from CAD files, BIM, DXF files, and adjust them in order to have a geometric representation. Obviously, it's very important to assign materials to the surfaces that you imported in your model. That information involves the acoustical absorption coefficient, also the scattering coefficient. Most programs come with a basic database of some basic default materials that can you use in specific cases, in a specific planning task. You obviously need more, let's say, applicable information from the manufacturer in case you're looking at specific products. You need to obviously insert sound sources. These sound sources, again, they can be provided by these applications in a default sense. Human voice or specific musical instrument. You can also generate typically sound sources by defining the sound distribution patterns, the three-dimensional distribution pattern, and also the overall sound power, and that way define your own sources. Then you set certain calculation parameters. This is the part where some experience, both in the foundation of the room acoustics is necessary, but also some experience with the applications that you happen to be using, transition orders, how many early reflections are you considering through the source image methods, and when you go beyond that, what do you do in terms of the number of rays and things like that. In these specific programs, it provides you a possibility to do a very quick estimate, for example, using the Sabine method. You can make some global estimates for the room as a whole, so get, so to speak, room-related mean values of indicators such as the reverberation time, but also you can, for the jobs that you have defined, so for the specific receiver points that you have defined individually or on a grid, you can then calculate in detail the value of a multiple performance indicator, as I mentioned before, such as, for example, the early decay time or the reverberation time, sound power levels, values, measures of clarity, and the speech transmission index, and so on and so forth. So they give you these values. What is also very useful to get a time domain representation of the arrival of the sound energy in terms of the first arrivals and arrivals that are distinct from different parts of the room. That helps you, as I alluded to before, identify potentially harmful reflections or geometric constellations that might, for example, give you late reflections that come at high intensity, so they may be perceived and hence they could be harmful to the overall acoustical experience. Mentioned before, you can define grade and then kind of pretty much analogous to visual performance simulation to get distribution of these indicators on a plane or in a three-dimensional sense. One very attractive feature of the advanced room acoustic simulation models is that you basically can use these reflectograms that shows how the space transforms the signal emitted by the sound source, that this computational transformation matrix can be auralized. So the idea is that you can apply the same manipulation to any signal that you introduce this model and basically use electroacoustic methods to make it audible so that you theoretically can put a headphone. A typical approach is to use a headphone and listen to how the space has changed the initial properties in terms of the frequency and strength of the acoustical impulse produced by the source. So that comes very close to actually a visual rendering as we do in visual simulation. So long before the building is or the room is constructed, you get a first feeling of the type of acoustical experience that you could be expecting. Of course, you could argue that the headphones not quite capture the directionality of the sound. This is a general well-known problem. So there are even specific laboratories that recreate this directional effect, not by using headphones, but by using a series of speakers and kind of emulate the behavior of a virtual room. So in terms of a kind of a virtual reality represented in acoustical sense. So that is a very attractive feature of the advanced room acoustic simulation model. So you can define such auralisation parameters and create, so to speak, these files that you can listen to for different positions in the space. Okay, this was a rather, so to speak, dense and somewhat brief. I understand that I talked about multiple issues only in terms of very short, so to speak, brief overviews, but I hope I could give you a feeling, in case you have not been in this field, a feeling of what are the main issues and what are the main possibilities. It appears to me that especially in the area of the room acoustics, maybe not so much buildings acoustic yet, but room acoustics, we have come a long way. Up till a few, I would say, decades ago, designs of successful room acoustics was a kind of a hit and miss endeavor. People would study historical spaces. I have here, for example, the great music, the Musikverein Saal in Vienna, is in my hometown, which has a great acoustics. So people will study these buildings and try to find what is the secret of, so to speak, this acoustics. And in many cases, people would do new buildings and the acoustic didn't satisfy or didn't meet the expectations. But it seems to me that in the last decades, due in part to advances in building physics and acoustics, but also the modeling techniques. It has become more of a dependable process in which, for sure, we can avoid basic issues. You could argue that maybe getting that ultimate quality maybe is still something that cannot be 100% designed, but for sure we can design spaces that avoid pitfalls, that avoid basic problematic issues, and provide a fairly reasonable or excellent room acoustics. Maybe one last concluding remark, which I should mention to complete this picture, is the uncertainty associated with acoustical simulation. As with all the other areas of building performance simulation, there's always the question is how good are we in terms of the predicting the real performance. That means if we design a building and later on we go and measure the performance, and in case of acoustics, it's actually quite convenient. It's much easier in a sense if you want than the thermal simulation predictions, because in order to figure out if your energy or temperature predictions are okay in a building, you need to look at longer periods of time and look at the interaction with climate and things like that. In room acoustics, it's fairly straightforward. You go into a room, put your sound sources in there, and you measure these indicators. So the question is, the testing of the validity and reliability of these models is not that difficult, but however the question is, what are the sources of uncertainty and what are the things that can go wrong in modeling? And there are a number of issues, obviously, like many other areas, if we have models that the integrity of the model is not satisfactory, if the geometry is not properly modeled. So that can be part of a problem. Another challenge is the correct specification of the acoustical properties of building components, which is also not trivial, especially if at the certain design stage you don't have the final information about what materials would be used and where they would be. So that introduces some uncertainty. Even for cases where we have been looking at the acoustical retrofit of existing buildings, and a lot of work in the room acoustic is also in that area, it is difficult, for example, to do in situ measurements. There are some equipment available where you can try to measure inside, but they usually are not so dependable, especially at low frequencies. So the uncertainties associated with the specific acoustical properties of the surface, the enclosure of the room, can be also another source of uncertainty. And then there are other issues like the experience of the user. If the user, and that is a bit of an issue that I would like to mention, if the user is not familiar with the foundations of acoustic, if he or she doesn't have sufficient field experience, it might be that they do a lot of things with regard to the setting in these programs. Those things might be opaque to them, and they may make some assumptions that are simply or not appropriate, and that may result in large deviations. My own personal experience is that in existing cases, when one does retrofit, it's always a very good idea to do some measurements and, so to speak, calibrate the simulation program. And we have done that in a number of projects, so that you look at the integrity of your model based on some measurements, and then once the model is calibrated, parametric studies of the things that you could do to improve the acoustics would be much more straightforward and also much more dependable. So I hope I provided with you with a brief overview, which hopefully also, in case you have not been in this area, maybe made it a bit more interesting for you to pursue in future. And I thank you for your concentration, and I'm available to Rajan and yourself in case there are any comments or questions. Thank you very much.
Very much, Ardeshir. So far, it was pretty intense and sort of new subject even for me. Very, very interesting to learn about a few things on acoustics. We have a question from AJ Rao. I have unmuted him so he can ask you a question. So far, we have only one question. Over to AJ Rao. Hello. Hello. AJ Rao. Can you hear me? Okay, it seems that I have unmuted him, but he is still on. Let me ask a question on behalf of him. The question is, Professor Madhavi, do you have any examples of successful gray box model for predicting sound transmission across assemblies? Is this emerging as a viable pathway to pursue prediction of the above?
Right, it's a very good question. You know, I personally have been involved in developing such gray box models for massive types of constructions, where we look at certain basic properties like the layout, basically how does the geometry work, the junction geometry, and some basic information about sound reduction index of components that are involved in the assembly and their density. And based on that, we can get fairly reliable estimations of the resulting sound level difference, the normalized sound level difference between these two rooms. In fact, in some countries, in European countries, they are already part of the standard, so you would have to apply those. And there are some simple computational tools that have adapted those. And some of those also have been already coupled with room acoustics, such that you can have both building acoustic related and room acoustic related calculations in the same environment.
Okay, is that good enough, Mr. AJ Rao? Is
Yes,
this fine?
can you hear me?
Okay. Yes, we can.
Yes, thank you, Professor Madhavi. First of all, a very interesting presentation, and I really hope that it elevates acoustics and acoustic modeling at in IBPSA. I know you said you've done some work on gray box modeling. Has there been any kind of published results on successful use of the models? And do you see that as a viable alternative for prediction, as opposed to pursuing a purely, say, a physics-based model?
Right, you know, one of our early publications in that area is in the Journal of the Acoustical Society of America. I can make maybe through Rajan a reference to that, but there have been many work also since then. And as I mentioned, those type of models are included in standards. It is, of course, you know, from the point of view of somebody who's excited about the possibility of numeric simulation. It is, of course, is somewhat unsatisfactory situation that we do not, it seems to me at least, are not aware of widely used first principle based models of, for example, airborne or impact noise propagation. I've seen those models being worked by researchers looking at maybe simple assemblies where you have a wall and you look at the sound emission by modeling the vibrational behavior of this wall and so on and so forth. But if you look at a more complex assembly, you know, involving multiple rooms and so on, apparently our computational capacities are still, you know, do not manage to address, especially for high frequencies, the frequency domain is a problem to address those. So I hope that those efforts, the research community would lead at some point to have first principle based models. Until then, a combination of the statistical energy analysis and these type of gray box models that use a combination of heuristics, measured information, empirical information, we have to, so to speak, work with those possibilities. For practitioners, they provide some useful tools, I would suggest.
That's very helpful, Ardashir. I think we don't have any other question coming from the attendees. So I wish to thank Ardeshir for one more webinar on IBPSA platform. Thank you, Ardeshir, and thank you all for attending the workshop and webinar.
Thank you.
Thank you.